two cases or two special cases for Routh array. The first one that you have 1 0 on the first column, and we already see how to deal with this case and how to solve or how to identify the system stability if you have 1 0 in the first column. So we already learned two methods, one using the epsilon method and the other one using the reverse coefficient method. Okay, the second case that you have the entire row of zeros. That means you have the one of the rows in the Routh table which equal to zero values. Okay, what we are going to do in this case, or if you have an entire row of zeros, that means all coefficient after this row will be zeros. I mean, if I have this, for example, in this Routh table here, for this Routh or for this row, which is of s equal to s to the power of 3, if I come to this row and I have this row, all element or all coefficient here equal to 0. The first one is 0, the second one is 0, the third one is 0. That means if I continue to construct Routh table, if I continue to construct Routh table here until the end, all these elements will be 0, 0, 0. Why? Because if you have one 0 in the determinant value, since our elements equal to determinant, so if this one is equal to 0, that one equal to 0, always your value will be 0, 0, 0. Okay? So what we are going to do here, we are going to solve this example and we see how we can solve the issue of existence of entire row of zero. So you have this transfer function or closed loop transfer function which consists from the zeros. There is no zeros here, and we have the numerator or characteristic equation which is s5 or s to the power of 5, 7 to s to the power of 4, 6 s to cubic, and 42 s squared, 8s, and so on. So in order to construct the Routh table for this equation, we need to write the first column here. So the first column is s to the power of 5 and then s to the power of 0 as usual. Okay, nothing changed. We are going to write the coefficient in the first and second rows. So the coefficient will start from the even coefficient because the highest is even number, odd number. So the highest is odd number, so we are going to write the coefficient for odd number. So this one is s of the coefficient of s of 5. This one is the coefficient of s cubic. This one is the coefficient of s of s. That one is the coefficient of s to the power of 4. That one is the coefficient of s to the power of 2 or s squared. That one is the coefficient of s to the power of 0 or the 56. Okay, so this is s of 0, s1, s squared, s cubic, s to the power of 4, s to the power of 4. Just we write the coefficient for this element. We write the coefficient. This is the first value that we have actually. I mean the original coefficient value. But we said if we can simplify, this is 7, that one is the 7 here. This one is 42, so that one is the 42. That one is 56, so this one is the 56. This is the original value. Okay. But if we said we can simplify, we can go to simplify because the simplification will make the calculation of the other coefficient easier. So the common element between these three elements is 7. So we divide by 7. So we got 1. We divide this one for 7. We got 6. We divide this one over 7. So we got 8. So our elements become 1, 1, 6, 6, 8, 8. Okay. So this become easier to calculate the rest of elements. When we try to calculate these elements, we use the determinant method. The first value that we have, 1, 1, our determinant will become in this form. So it's become like the determinant in order to find this element here in this part. If I want to find the element of this s cubic or the coefficient of s cubic, our determinant will be like this one. It will be the first column or the first column here, which is 1, 1. Okay, so just I put 1, 1, and the second will be the second element, which will be 6 and 6 here. I put 6, 6. This is our determinant, the negative value over the element which is the second element on the second column here, so it will be on the first column, so it will be 1, so divided by 1. If you open this element, it will be 1 times 6 minus 1 times 6, so it will be 0 value. So this will be the value here, which is 0. If you go to the next one, and the next one will be the determinant, it can be calculated, the next element can be calculated from this determinant, which is as usual negative. Okay, then the first element is the same, the first column it will be 1 1, and the second element will be this, will be, you can see 1 1, then the second for the first element will be 6 6, the second for the second element will be 8 8, so it will be 1 1 8 8 over near the value of the first element, which is 1, okay, over 1. So if you open this one, 1 times 8 minus 1 times 8, it will be also 0. So you got this value, which is 0. You go for the third one element, also you are going to get the same value, which is 0, because you have 1 1 and you have 0 0, so the result will be 0. So now we have entire row of 0. This is the row of 0, star 0 0 0. Since you have the entire row of 0, so this is the second special case of Routh array or Routh table. Okay, so how we cannot decide, or we cannot continue. If we continue with this value now, 0 0 0, we continue to calculate the second coefficient here for s square. This for sure becomes 0. Why? Because they have 0 here, 0. So I mean, if I want to calculate this element here by using the 0 values, I will have this one 1 0, and they have the other one will be 6 0. So this become also 0, that one also becomes 0, that one becomes 0, all become 0 0 until the end. Okay, so if you have all 0, it's not easy to say I have positive to negative change or negative to positive change. So what is the solution here? In order to solve this issue, actually we need to deal with this situation. Key eraser. So in order to find this, to solve or to overcome this issue here, we need to deal or to have some special solution for this case. So the special solution will be how to remove this entire row of 0 in order to continue calculate the rest of the variable or rest of coefficient uh, of our Routh table. Okay, so what we are going to do here, we have to go one step before the line or before the row of the that give you the 0 value. Okay, which one step? That means the row that give you the 0 values is this row, which is s cubic, correct? Since I have the row which give me the 0 values is the s cubic row, I go one step before, I go to the row of s to the power of 4. What should I do? I need to write the equation of this row. So the equation of this row represent the coefficient times the value of s. Okay, so now we said this is the coefficient of s to the power of 4. This one is the coefficient of s to the power square, s square, and this is the coefficient of s to the power of 0, correct? So I can write the equation for this row, which is s4 times 1, that means s4 plus 6s squared plus 8. So this will be the polynomial equation or the auxiliary polynomial equation for my or for the previous row of to the entire row of 0. This is the row of 0. I go one step before or one row before. I write this equation. PS equal to S4 6s squared plus 8. So this is the coefficient 6 8. I put here S4 S squared because we said this row is for the even number or the even degree or the even order of the S, and this one is the odd, correct? So if I want to write the equation for the first line, it will be like S5 plus 6s cubic plus 8 S. The equation for this line is S4 plus 6s squared plus 8. Okay, so now this is the equation. we need to apply the differentiate of this polynomial. So we find the derivative of this equation. So the derivative of the exponential of the equation with the power, for example, here s to the power of 4. If I'm going to take the if I want to drive s to the power of 4, okay. So the derivative of this one to the value of s, it will be 4s cubic, okay. So it will be 4s cubic. I drive the polynomial here, the derivative of this one, it will be 4s cubic. The derivative of this one will be 2 times 6, it will be 12s. The derivative of 8 becomes 0. So I have new equation here, or new polynomial here, which is 4s cubic plus 12s plus 0. So this coefficient here will be replaced the 0 line. So I mean the new polynomial with the coefficient for s cubic, s, and s to the power of 0 here will be replaced to the line of zeros. So I will take the 4 coefficient, I put it here for s cubic. Now we are talking about s cubic, correct? So the coefficient of s cubic here will be 4. I'm going to take this 4, which is the coefficient of s cubic, I put it here. What is the coefficient of s to the power of 1? This is s cubic. This s to the power of 1, it will be 12. So I'm going to take this 12, I put it here. Then I'm going to take this 0 and put it here. Okay, so now I do not have entire row of 0. I have values here. I have 4 and they have 12 and they have 0, only one 0, not entire. So this not 0 anymore. This element not 0 anymore. Okay, so I have 4, 12, and 0. Now I want to simplify. I just divide by over 4. So 4 over 4 become 1. 12 over 4 become 3. 0 over 4 become 0. Okay. So this will be the new row that I have by applying this auxiliary polynomial method. Okay. Since I have now 1, 3, 0, just I continue to calculate what is the value or the coefficient for s square as I did in the previous example. Just you need to find the the determinant, same like we did before for this element, for that element, and so on. We continue to calculate that or to construct the Routh table. Now the entire row or the all element in row 1, there is no zeros, so I have only 1, 1, 1, 3, third, 8. So all the coefficient in or all the element in the first column of the Routh table here are positive. So 1 is positive, 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 positive. Since all elements are positive, that means there is no change in the sign of elements in the first column. So there is no change in the sign, that means our system is stable. So this system or the transfer function of that system or the system which is represented by this closed loop transfer function is stable because there is no change in the sign of the element in the first column. Since there is no change in the sign, that means all poles are located on the left half plane, so no poles on the right half plane, so our system is stable. Okay, so this is how to deal with the entire row of zeros. You go one step before, you write the equation for the row before the entire row of 0. After you write the equation, you drive this equation for s. So you take the coefficient, you substitute in the row of zeros. How to, what the coefficient, start from the coefficient of the highest order to the coefficient of the lowest order. Then you continue construct your Routh table, and then you decide is your system stable or not. Okay, now we have another example, and this example is actually important to show what is the impact of the gain value, which is the gain. We said the gain if you have a constant in the numerator of your transfer function. So this we call it the gain value. So the gain of your transfer function, what its impact on the stability of the system. The gain actually, or the value here k, will be used to adjust the stability of the system, so we can achieve the system stability by changing the value of k or the value of the gain of our system. Okay, the gain of control system. So how we can adjust this gain? Actually, the gain or the value of the gain, or how this value of the gain can affect the system stability, we will see here. By using the Routh table, we are going to build or construct the Routh table for this transfer function. Then we are going to see which value of k will make the system stable, which value of k will make the system unstable, which value of the k which make the system marginally stable. Okay, usually the value of the gain assumed to be positive. That means greater than 0. We cannot say the gain is -1, the gain is -2. So the gain always assumed to be positive values. Okay, so now this transfer function actually is open loop transfer function. This is the transfer function of the open loop, but we have a feedback here, which is make the system unity feedback. Since we have unity feedback, we need to calculate the value of TS before we go to build our Routh table system. So TS will equal to GS over 1 plus GS. Since HS equal to 1, so HS is there, but it's 1, so it's just omitted from the equation. So we have GS over 1 plus GS. So we are going to find TS first. After we find TS, we are going to identify our characteristic equation. Then we are going to solve or to build our Routh table to identify how many change in the sign of the first column elements. Based on this change, we will decide is our system stable, our system unstable, our system is marginally stable. So as we can see here, this will be the closed loop transfer function that we found it by using the equation GS over 1 plus GS. So you solve GS over 1 plus GS, you got this equation. Okay, so this we call it the closed loop transfer function. Okay, since this is the closed loop transfer function, this part of the closed loop transfer function, we see the denominator represent our characteristic equation. Now we are going to use this part or characteristic equation to build our Routh table like we did before. So the highest s to the lowest s, so start from s to the power of 3 until s to the power of 0. We write in the first column the element or the coefficient of the s, the even, the odd and the even. So in the first row is the odd because the first is s cubic. So we start to the coefficient of the odd. So the coefficient of s cubic is 1. The coefficient of s is 77. Just we put 1 and 77. Okay. Then we go for the second line, which is even, which is start from s cube s square. The coefficient of s square is 18. The coefficient of s0 is k. Just we put it k as it is because it's given as a k gain value. We don't know what's the value of the gain. This value will be changed, so we just put it k. Then we calculate the rest of the elements for our Routh table. How we found this one? From where we got this 1386? Actually, we make the or we apply the formula which said that negative determinant of the previous column. Okay, so it's 118. This is the first element. The second element will be 77 and k. 77 and k, and divided by the element here, the second element, which is 18. Now you open this one, it's become like 1k minus 77 times 18. So it will give you 1386 minus k. After you divide it by then 1386 minus k divided by 18. So this is the 18 that we divide by it. Okay, so this will be the first element. The second element here will be 0. Why 0? Because I have 77, I have 118. The second, this 0 come from 1 18, and the next after 7 7 we do not have any element, so it becomes 0 0. So negative over 18, so it's become 1 times 0, 18 times 0, so all equal to 0. So we have 0 here. Same is for the second one here. So now we need to find this one. So this value will equal to 18, 1386 minus k over 18. This is the first column. The second column will be k and 0. We multiply, we open, we find the value is equal to k after we open the determinant. And the second element here becomes 0. Okay. So now we do not have any 0 in the first column, correct? All the value here are there, no 0. So we do not need to apply any of the special case for the Routh array. So we just check the sign here. If I check the sign of the first element is positive. This one is positive. For 18 is positive. For k is positive because he said in the question the value of k is greater than 0. Greater than 0, that means the value of the k is positive. Okay, so the k is positive. Now we need to know what is the sign of this magnitude or of this value. We cannot say it is positive, we cannot say it's negative, because this value here or the sign of this value depends on the value of k. Since k is greater than 1, it is positive, but we don't know how is or what is the value of k. So this element will decide the stability of our system. Okay, so depends on the value of k. Is it greater than 1386 or less than 1386 or equal to 1386? We will have three situations. Okay, if you have this element here, 1386 minus k over 18. Okay, now if I put this value equal, if I want to solve this equation for the value of k, so I have three situations. The first situation, if k is positive and it is greater than or it's equal to 1386, so what will be this magnitude? It will be 1386. If k equal to the same value, which is 1386 over 18, so the value of this element will be equal to 0. If the value of this element is equal to 0, that means I have 1 0 in the first column, so I need to apply either epsilon method or the reverse coefficient method in order to decide the stability of my system. So this is one of the situations. The second situation, the value of k is positive, but it is less than 1386. That means it can be 100, it can be 1385, it can be 1000, it can be 1900, any value, but less than 1386. If the value of k is less than 1386 minus k over 18, and the value of k is less this value, so this will give you a positive value. Why? Because k is less, so positive minus the value which is less here, it will give you a positive value. And in this case, if this magnitude is positive, that means this will become positive, so our system becomes stable because no change in the value of the sign of the first column element. The third case will be k is greater than 1386. That means this value, which is 1386 minus k over 18, assume k is equal to 1400. So if it's 1400, for example, the result here will become 1386 minus 1400. It will give you negative value, which is negative 14, for example. Since it is negative 14, so the sign of this magnitude or of this element become negative value. If the sign here is negative, that means you have one change from positive to negative, one change from negative to positive. So you have two change. Since you have two change, that means you have two poles on the right half plane. Since you have two poles on the right half plane, that means your system is unstable. Okay, so these are the three cases depends on the value of k. The first k is positive, I mean in all cases k is positive greater than 0, but it can be greater than 1386, it can be equal to 1386, it can be less than 1386, and for each situation the stability of the system will be changed. For that we said k is used to control the stability of our system. Okay, so this entry can be positive, 0, or negative. Positive if k is less than 1386. If k is less than 1386, so it will be positive. If it's positive, so our system will be stable. If k greater than 1386, like we said, 1400, 1500, and so on. So in this case, this column will be a negative. If the system is, if the column is negative, that means we have to change from positive to negative, from negative to positive. So our system will be unstable because we have two poles on the right half plane. And the last case is k is equal to the value of 1386. So we have 1386 minus 1386 over 18, it will give you 0. So if you have a 0 here, that means we cannot say it is positive or negative. So we need to apply one of the method that we learned before to solve. Either we use epsilon or we use the reverse. Okay, so we can see here in the case of k equal to 138, we have the entire row of zeros. Sorry, actually, it's not 1 0 only, because we have only two elements here. You can see if this one becomes 0 and you already have this another 0, so you have entire row of 0. It's not one element. We cannot apply the epsilon or the other method. In this case, we need to apply the entire row special case. Entire row special case because we have 0 here and we have a 0 there. Okay. So in this case, we will see here, we need to apply the entire row of 0 because this one is 0 and that one is 0, correct? In the case of k equal to 138, this line becomes 0, that I mean this element and that element becomes 0, so we have entire row of 0. So what we need to do, we go one step before, which is the previous line. We write the equation, which is 18 s squared plus 1386 s to the power of 0. This will equal to 0, or this is the will be the our equation or the polynomial of s. Okay, then we drive this polynomial of s to s, so it become like 2 times 18, it will become 36s plus 0 equal to ps here, I mean dps over ds. Okay, so we have 36s plus 0, so we need to write this 36s plus 0 here. So we write the 36 and 0 in this line. So this is the new elements that we have. Then we continue to find the next element, which is we can find it, which is 1386. Since it is 36, so we have positive, 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 positive here. So our system will become stable with two poles are located. Since we have here the entire row of 0, it means that we have some poles will be located on the imaginary axis. If you have some poles on the imaginary axis, that means are here, are not on the right, the system is still stable because it has, how many poles do we have here? We have the number of poles are 3, correct? Because the highest, the number of poles is equal to the highest order of s. Since we have 3 poles here, we have one pole will be on the left side and we have 2 poles on the imaginary axis. So we do not have any poles on the right, so the system is still stable, but it's marginally stable at these 2 poles. Okay, since there are no sign change here from the even polynomial s square row down to the bottom of the table, that means we have two roots on the j omega axis or on the imaginary axis of our system, and these two rule actually, or these two poles will give you the marginally stable situation. That means our system is still stable, but it is marginally stable. Okay, it's not absolutely stable. Okay, so this is how we can study the impact of changing the gain from positive value to, I mean, from small value to high value, and by changing the gain we can change the stability of our system. So this, the gain of k here, give you three situations. Give you the first situation is the if the gain is less than 1386, so your system is stable, absolutely stable. Then the second situation, if the gain k is less than I mean is greater than 1386, so your system is absolutely unstable because there is roots on the right side. The third situation, which is k equal to 1386, and this gives you a row of zeros, and we calculate that we have two poles on the imaginary axis, which make your system is marginally stable. So this is important. Actually, you need to solve the existing examples and exercise in class exercise in order to practice more and to understand how the value of gain can change the system stability.